So let's talk about Pauli operators. They are really useful. I mean, really useful. They help us to identify code subspaces, they help us to identify errors, they help us to identify unitary operations on logical qubits. They're really useful. Sometimes I just wonder, what would we do without Pauli operators and Pauli matrices in physics? Anyways, so when I say a Pauli operator, I mean a tensor product of Pauli matrices, including the identity. So a Pauli operator on n qubits is n-fold tensor product of Pauli operators, including the identity. So for example, if I have 3 qubits, here's one Pauli operator, identity, tensor z, tensor x. Quite often, when it's clear from the context that we are talking about tensor products here, you just write it as identity zx. We just drop the tensor product sign. Or if you want to go for even more compact notation, you'll find it a lot in the literature. you can write it as z on the second qubit, x on the third qubit, and so on and so forth. So Pauli operators have a number of interesting mathematical properties. For example, well, I mean, we're not going to go into all details, but if you multiply 2 Pauli operators, you'll get almost another Pauli operator. So when I say almost, because if you multiply, say, x and z, you'll get minus I, y. So there's this phase factor here that you have to take into account. So plus I or minus I if you want to have a close algebraic structure when you multiply Pauli operators. So a Pauli group is composed of Pauli operators, including the phase factors plus I and minus I, and plus 1 and minus I, just to guarantee the closure of the whole algebraic structure. Now, when I say Pauli operator, I refer to a Pauli operator proper, with the prefactors either plus 1 or minus 1, a Hermitian one, right? So Pauli operators are unitaries. They can describe evolutions, physical evolution. They also Hermitian. They can describe observables. They can describe measurements. If you pick up any Pauli operator that is not the identity, the trace of this Pauli operator is equal to 0. Why? Well, it is a tensor product of Pauli matrices. We know that the trace of any Pauli matrix except the identity is equal to 0. So, and we also know that a trace of tensor product is a product of traces. So clearly, the trace of any Pauli operator is equal to 0. Now, Pauli operator square to the identity. So that means that there are only 2 possible eigenvalues, which is plus 1 and minus 1. The 2 facts, the 2 properties are actually quite important for us. So if we consider a Hilbert space associated with n qubits, that's another potato of mine. So my potatoes always describe Hilbert spaces of many qubits. And so if you then have a Pauli operator, say E, acting on this space, this Pauli operator will bisect, will split the Hilbert space into 2 subspaces of equal dimension. Those will be eigenspaces associated with eigenvalue plus 1, and this one associated with eigenvalue minus 1. And they are of the same dimension. Why is that so? Well, going to the basis in which E is diagonal. And then if you look at the matrix of E, then you'll see plus or minus 1. You see the eigenvalues on the diagonal. But because the trace is equal to 0, then that means that the number of plus 1s and minus 1s is the same, right? So that means that the eigenspace associated with eigenvalue plus 1 has the same dimension as the eigenspace associated with eigenvalue minus 1. This is actually quite a useful property that we will use to identify the code spaces and the error subspaces. So we just pick up one particular Pauli operator that will bisect the Hilbert space in one way. Then you just pick up an orthogonal or linearly independent Pauli operator that will bisect the whole Hilbert space in in a different way. So we'll have, say, eigenspace +1 and -1 of this new operator. So let's call this one E1 and call this one E2 here. So then you can associate different labels with those subspaces. So for example, you have a subspaces label +1 +1. So that would be this subspace. And then we will be choosing this kind of a subspace as our code subspace. And then you can clearly see that those operators here will just define the error syndrome, because whenever error happens, we'll just move to another subspace, which will be then labeled by, if you think about those operators now as a sort of observables, and the outcomes of the measurements are +1 or -1, then you will have a subspaces label as, so this one would be +1, +1, then this one would be just -1, +1, and so on and so forth. So you can, each outcome of the measurements of say E1 and E2 will give you, will identify in which subspace you are. So this way we'll be finding where our state is after, say, error happens. So you just identify the code space, and error will happen. That will be another Pauli operator that will just describe the error, the movement within the Hilbert space between the code subspaces. So we have then Pauli operators that play the role of the measurement, the error syndrome measurement. They will form an interesting subgroup which we call the stabilizer. So the code subspace will be just defined by specifying as sort of a subgroup of Pauli operators that stabilize this subspace. We'll talk about this in a moment. Now, going back to mathematical properties, any two Pauli operators, if you pick up any two Pauli operators, they either commute or anti-commute. So if you pick up E1 and E2, the product E1 times E2 is equal either to E2 times E1 or minus E2 times E1. There's no third option. A very useful property that we again use a lot when we construct a good error correcting codes and play with Pauli operators. So now coming back to this diagram, in a moment I will actually give you a specific example. We'll go back to our 3-qubit repetition code, and I will show you how different Pauli operators specify code subspaces, error subspaces, errors, and also logical operations. But just to give you sort of a general overview, any Pauli operator will have a role to play in a scheme of a quantum error correcting code. Some Pauli operators will specify, as we talk, will just specify the code subspace and the error subspaces, and that kind of operators will form a group called a stabilizer. Then there will be errors, Pauli operators that describe errors, so how you move between different subspaces. And there will be also Pauli operators that describe not movement between the subspaces, but movement within the subspaces. This is sort of defined by the stabilizer. And those operators will form another group that we'll be interested in. It's called a normalizer. Or in this case, it will be just equivalent to something that is called centralizer. As it happens in this particular case, the two are the same, even though they're two different mathematical concepts. So never mind. So I'm just sort of using some mathematical name dropping, well, the sort of term dropping, I would say, but I will explain what it means in a moment. But just to give you the idea, pick up any Pauli operator, and they usually are either responsible for specifying the subspaces in which we are going to divide our Hilbert space, or they are responsible for describing errors, so how we move from those subspaces to another subspace, or they are responsible for describing logical operations, so on the evolution of on an encoded qubit. So that's the operations within those subspaces.